Now in this section, we're going to look at some limits involving infinity. Here's the graph y equals 1 divided by x. Now notice the notation here. The limit as x approaches negative infinity and the limit as x approaches positive infinity. Now that's not implying that infinity or negative infinity are actually numbers. What this is saying is what happens to this graph as x gets infinitely small or as x gets infinitely large. So as our numbers get smaller and smaller and smaller, our x values, what does our y values approach? And as you can look here, as we get smaller and smaller x values, our y values tend to approach 0. So the limit as x approaches negative infinity of 1 over x is 0. As our x's get larger and larger and approach positive infinity, you can see that again our y values tend to approach 0. So the limit as x approaches infinity of 1 over x is 0. And again, that's not saying that infinity or negative infinity, either one are actual numbers. It's just what happens as our x's get infinitely small or infinitely large. Now this should make sense to you if you think about your denominator of your fraction, 1 over x. The denominator is becoming larger and larger and larger and larger. And as you divide by larger and larger and larger numbers, the 1 over x becomes smaller and smaller and smaller and will approach 0. Now all the limit laws that we've seen up to this point are true when we replace the limit as x approaches c by the limit as x approaches infinity or the limit as x approaches negative infinity. So x can approach a finite number such as c, or it can approach positive or negative infinity. Now let's look at the limit as x approaches infinity of 5 plus 1 over x. Now remember, the limit as x approaches infinity of 5 would be 5. And we just saw that the limit as x approaches infinity of 1 over x is 0. And 5 plus 0 is 5. So as x gets larger and larger and larger, this will become close to 0. So 5 plus 1 over x will become close to 5. Now let's consider this function, y equals 5x squared plus 8x minus 3 divided by 3x squared plus 2. If you look at the graph, as you go towards negative infinity and as you go towards positive infinity, this appears to approach the line 5/3. Well, let's think why that should be the case. What we can do as we examine this limit is we look at the leading term on the top and bottom and choose the highest variable exponent term, which is x squared. And what we'll do is we'll go through and we'll divide every term on top and every term on bottom by x squared. So I'll take 5x squared and I'll divide it by x squared. I'll take 8x and divide it by x squared. And I'll take negative 3 and I'll divide it by x squared. In the denominator, I'll take 3x squared and divide it by x squared. And I'll take 2 and divide it by x squared. Now, I can do that as long as I do everything, the same thing to everything in the numerator and everything in the denominator. So this gives us the limit as x approaches infinity. And here your x squareds will cancel and you will have 5. Here, remember our quotient rule, we subtract 2 minus 1 is 1. X in the denominator, x to the first power in the denominator. Cannot simplify 3 over x squared. In the denominator of the fraction, our x squareds cancel and we'll have 3, and then I cannot simplify 2 over x squared. Now, if you think about what happens as each one of these denominators become infinitely large, 8 over x, 3 over x squared, and 2 over x squared are going to become closer and closer and closer to 0. So this limit is going to be 5 plus 0 minus 0 divided by 3 plus 0, or 5/3. So as our x's get larger and larger and larger, then our y's are going to approach the line y equals 5/3. Now let's take another example. This is the graph of y equals 11x plus 2 divided by 2x cubed minus 1. And let's think about what happens as our x's become larger and larger and larger. So as our x's approach infinity. Again, we look at the leading term on the top and bottom, and we choose the one with the highest variable exponent, which is x cubed. That means we're going to take and divide every term, top and bottom, by x cubed. 11x over x cubed, 2 over x cubed, 2x cubed over x cubed, and negative 1 over x cubed. Now, as we simplify each one of these, we'll have the limit as x approaches infinity of 11 over x squared plus 2 over x cubed, all divided by 2 minus 1 over x cubed. Now remember, as the denominators get larger and larger and larger on these three fractions will approach 0. So we will have 0 plus 0 in the numerator and 2 minus 0 in the denominator. And 0 divided by 2 is 0. You'll notice from the graph that supports this as our x's get larger and larger and larger, our graph tends to approach y equals 0. Now these lines where our graph tends to almost flatten off or get closer and closer to as we go out towards negative infinity and positive infinity, we call those horizontal asymptotes. Remember, a line y equals b is a horizontal asymptote of a graph of a function f of x if either the limit as x approaches infinity or negative infinity of f of x is b. And so that's what happened with each of the previous examples. As our limits approached infinity, our graph approached a finite number. Here's another example of a graph with a horizontal asymptote. The one thing to notice about this is that this curve actually crosses the horizontal asymptote, and it will cross it an infinite number of times, and that's okay. Your graph can cross a horizontal asymptote, but the horizontal asymptote here is 2. Now let's think about why it's 2. Obviously the limit as x approaches infinity of 2 is 2. So let's think about the limit as x approaches infinity of sine x divided by x. Now sine x is always going to be a number between negative 1 and 1. And our denominator x is going to get larger and larger and larger. So we have numbers between negative 1 and 1 divided by larger and larger numbers. So this will also approach 0 as x gets larger and larger and larger. So this graph will approach 2 as we approach infinity.